In part 3 of section 12, we're going to discuss in detail the way to graph a quadratic function. So Theorem 12.1 is going to give us some valuable insight into the graphing of a quadratic function. It says, let f of x be equal to ax squared plus bx plus c be the equation of a quadratic function. Number one, the graph of a quadratic function is parabolic shaped. Now the reason why that is the case is because of what we saw in the very first portion of this section. If I let a be equal to 1, b be equal to 0, and c be equal to 0, then we're going to end up with the equation f of x equals x squared, which we know as the squaring function. And the shape of the squaring function is a parabola. So every single quadratic function is going to end up having this parabolic shape to it. It'll be up to us to determine where is the vertex located, will there be any kind of stretching or shrinking, things of that nature. The second thing I want to mention here about the graph of a quadratic function is that there's only two directions that a parabola can face. A parabola is either going to open up, and that would be true if the a value is greater than 0 for your equation, and your parabola will open down if the a value is less than 0 in the equation that you're looking at. This is not a brand new concept though. This is analogous to the idea of reflection over the x-axis. We saw the idea of reflection over the x-axis when we talked about transformations in section 4. So that's precisely what this is. So if it opens up, then there is no reflection. If it opens down, then that means that we do have a reflection. And then the third thing I want to mention is the axis of symmetry. And you will routinely see me abbreviate axis of symmetry as AOS, and please feel free to use that as well. And the axis of symmetry of a parabola is the vertical line that passes through the vertex. So again, if we're looking at, say, the just the traditional squaring function, then the traditional squaring function we know has vertex at the origin. It has that parabola shape to the right and to the left. And if I had done this on a more suitable scale, then we would be able to see that the axis of symmetry ends up being the y-axis. So the idea here is that if you were to plot this on a piece of paper, you could then fold the piece of paper on that dotted line, and the two halves, the right and the left half, should end up mapping exactly on top of each other. They match exactly. And every quadratic function has an axis of symmetry, but it's not always going to be the y-axis. It's going to depend on where the vertex is located.